Hello everyone, welcome to the presentation on the paper Real-Time 3D Reconstruction and 6-DoF Tracking with an Event Camera, offered by Stanford Scholar Initiative. So what exactly is an event camera? It's a camera system developed at ETH and UZH, which is inspired by the human retina system. Unlike a traditional camera which outputs frames at fixed time intervals, an event camera outputs events asynchronously at microsecond resolution. An event comprises of the time at which it occurred, the pixel location at which it occurred, and the sign of intensity change of the pixel. Take a look at the advantages and disadvantages offered by event cameras over traditional cameras. Some of the primary research questions the paper is trying to answer are 1. 3D reconstruction and 6 degrees of freedom tracking using an event-based camera. 2. Novel techniques must be applied for event cameras. So why are these problems interesting? Identification of depth from a 2D perspective is important for self-driving cars. While several algorithms have been found, algorithms that are faster and use cost-effective hardware are still a topic of research. The paper proposes a method for real-time 3D reconstruction from a handheld event camera without use of any additional sensors. The authors present an algorithm to perform joint estimation of 3D scene structure, 6-DoF camera motion, and up-to-scale scene intensity from a single handheld event camera moved in front of an unstructured static scene. The authors use the algorithm to estimate camera motion, scene log intensity gradient, and scene inverse depth to solve the problem with simultaneous localization and mapping. The mapping part is separated into gradient and inverse depth estimation, ignoring the parallax effect. It can be used for high-speed robotics, 3D reconstruction, and depth from a single camera. The authors also believe it could be used for making real-time, high frame rate HDR videos. As stated previously, the authors used the algorithm to create 3D models of real objects and to tell where the camera is with respect to the world. Now let us describe the method used by the authors to approach the problem. An input stream of events is taken by the event camera and is processed one by one. Then, to regularize the noise in the frames due to camera motion, a weighted average filter is used. Camera pose and camera motion is estimated using an extended Kalman filter. Once pose estimation is done, log intensity and inverse depth values are computed. Using pixel-wise estimation based on EKF, using this, a reconstructed intensity and inverse depth value are obtained for each event frame. Finally, a 3D representation for the image is constructed using few selected frames. This completes the basic overview of the algorithm. In the experiment, the algorithm tracks against and reconstructs single keyframe for various indoor and outdoor scenes. 3D reconstruction is generally good, but poor quality depth estimates are observed through near boundaries. For multiple keyframes, the authors test the system on multiple trajectories. The authors render video frames from event data based on the method of ray casting. Let's look at the tracking performance of the system. The authors perform a qualitative comparison with a conventional camera for rapid motion. The top graph shows the estimated pose history, and the insert below shows the event visualization, rendered video frame, and the reference frame from the conventional camera. Note that motion blur is observed in the conventional camera, unlike the event camera. The algorithm produced allows for various outputs from the event input. It produces real-time, high-bandwidth 6-DoF camera tracking, a scene depth map, and a high dynamic range reconstructed video sequence at a user-chosen frame rate. Now let's discuss some limitations to the approach proposed by the authors. 1. Accuracy of tracking depends on the interaction of the three aforementioned probabilistic filters. 2. Slow convergence of inverse depth estimates could lead to poor tracking. A possible solution proposed by the authors is to use batch processing of events instead of processing individual events. With this, our talk now comes to an end. Check scholar.stanford.com for more talks. Thank you for watching.